The key to understanding pressure is to know that pressure is weight. For example, if you were to invite a hippopotamus to come and sit on you, your body would be subject to a pressure equal to the weight of one hippopotamus. At sea level, our bodies are subject to a pressure equal to the weight of the air above us. How much is this? If you were to take a column of air, 1 centimeter square, that extended from sea level all the way up to the upper reaches of the atmosphere, it would weigh 1 kilogram. A similar column of air, with a cross-section of 1 square inch, would weigh just under 15 pounds. What this means is that, at sea level, the surface of our bodies are subject to an atmospheric pressure equal to 1 kilogram per centimeter square, or a little under 15 pounds per square inch. We refer to this amount of pressure as either 1 bar or 1 atmosphere. You don't have to be much of a math whiz to figure out that when multiplied by the surface areas of our bodies, this works out to several tons of pressure. That's one very serious hippopotamus. So why doesn't this immense amount of pressure cause us excruciating pain or crush our bodies like eggshells? The answer is that our bodies are comprised primarily of solids and liquids, which are relatively incompressible. These solids and liquids also transmit pressure evenly, so it means that our body tissues are pre-pressurized at sea level to a pressure of 1 bar or 1 atmosphere. This also means that a state of equilibrium exists between our bodies and the pressure surrounding them, what we refer to as ambient pressure. So long as this pressure remains in balance, we won't feel a thing. Our bodies also contain a number of air spaces, such as our lungs and sinuses. However, so long as we keep these air spaces filled with air at ambient pressure, they'll suffer no ill effects. In fact, this helps explain how scuba equipment works. By allowing us to breathe air at ambient pressure, regardless of depth, scuba equipment allows us to breathe as effortlessly underwater as we do at the surface. Once we venture underwater, our bodies are subject to the weight of not only the air above us, but the water as well. Water is approximately 800 times denser than air and weighs considerably more. In fact, a column of water, just 10 meters or 33 feet high, is equal in weight to a column of air with the same cross-section that extends all the way up to the upper reaches of the atmosphere. What this means is that by the time you venture just 10 meters or 33 feet below the surface, the ambient pressure will have doubled. By the time you reach 20 meters or 66 feet, that pressure will have tripled, and by the time you reach 30 meters or 99 feet, the pressure will be 4 times what it was at the surface. Again, so long as we can keep the pressure inside our body's air spaces equal to that of the water surrounding us, we'll suffer no ill effects as a result of this tremendous increase in pressure. In fact, just as our bodies don't tend to feel the pressure of the atmosphere above us at sea level, they won't feel the water pressure when it's 2, 3, or 4 times greater. As divers, we're less concerned with the quantity of the pressure surrounding us than we are with its effect on factors such as volume and density. Here's an example that will better illustrate the relationship between pressure, volume, and density. For this example, we'll use an inverted drinking glass that's filled with air from the surface. At sea level, the pressure inside the glass is the same as the air surrounding it. That's 1 bar or 1 atmosphere. The volume of air inside the glass we'll say is 1 liter. And finally, we'll give the air molecules inside the drinking glass a density factor of 1. Let's see what happens when we take the glass to a depth of 10 meters or 33 feet. At this depth, the ambient or surrounding pressure is 2 bar or 2 atmospheres, twice what it was at sea level. The air inside the glass has been compressed to half what it was at the surface, showing an inverse relationship between pressure and volume. What's important to understand is that although the volume has changed, the quantity of air molecules has not. They're simply packed twice as close together as they were before. Now let's see what happens when we go to a depth of 20 meters or 66 feet. At this depth, the ambient pressure is 3 times what it was at the surface. The volume is now 1/3 of what it was to start. And the density of those air molecules is now 3 times what it was to begin with. At this point, you should have a pretty good idea of what will happen if we take the glass to the recommended sport diving depth limit of 30 meters or 99 feet. At this depth, the ambient pressure is 4 times what it was at the surface. The volume of the air inside the glass has been compressed to 1/4 of what it was at sea level. And, not surprisingly, the air molecules inside this tiny space are packed 4 times closer together than they were at the beginning. In your study materials, you'll find a chart that summarizes the information we've just discussed. You'll want to study this chart, not so much to commit it to memory, as to be able to recreate it by following the logic on which it's based. As divers, the relationship between pressure, volume, and density impacts us in a number of ways, which we'll discuss in the sections ahead. One very immediate effect of the increased density of the air we breathe underwater is how it affects air consumption. Case in point, at a depth of 10 meters or 33 feet, the air we breathe from our scuba cylinders is twice as dense as it would be on the surface. This means that at this depth, we'll consume air twice as fast. At a depth of 20 meters or 66 feet, we'll consume air 3 times as fast. And at 30 meters or 99 feet, we'll consume it 4 times as fast as we would at the surface. Let's look at this another way. How long a cylinder lasts underwater depends on a variety of factors, such as cylinder size and respiratory rate. Nevertheless, all other factors being equal, a scuba cylinder that would normally last us 1 hour at the surface will last just 30 minutes at a depth of 10 meters or 33 feet. The same cylinder will last just 20 minutes at a depth of 20 meters or 66 feet, and just 15 minutes at a depth of 30 meters or 99 feet. You already know that in shallow water, you enjoy more sunlight and brighter, more natural colors. Now you see that there's another very practical benefit to staying shallow whenever possible. Your air lasts longer. In the sections ahead, you'll learn about 2 additional limitations associated with deeper diving. For now, it's enough to know that it's to your benefit to stay shallow whenever possible.